Welcome everybody to the webinar of today. The speaker of today is Hassan Nagib, and he's going to talk about wall-bounded turbulence, recent lessons from Experiments-Asymptotics-Computation. So as usual, I introduce the speaker very briefly, and then I leave him the floor. So Hassan Nagib is the John Retagliata Endowed Professor of Mechanical and Aerospace Engineering at the Illinois Institute of Technology, and was the founding director of the Institute's Fluid Dynamics Research Center. His field of specialty is in fluid mechanics, turbulent flow, and flow management and control. At Illinois Tech, he served as MMAE Department Chair, Dean of the Armour College, Academic Vice President and Chief Scientist of IIT Research Institute. Nagib is the recipient of several prestigious honors, including being a Fellow of the American Physical Society and the American Association of Advanced Science, the American Institute of Aeronautics and Astronautics, and the American Society of Mechanical Engineers. From his base institute for more than half a century, he has been a visiting faculty on several occasions at Stanford University, California Institute of Technology, KTH Royal Institute of Technology, École Polytechnique Fédérale de Lausanne, Friedrich Alexander University, Erlangen, and Tewksbury Fellow in the Department of Mechanical Engineering at University of Melbourne. So it's with great pleasure that we have here today Hassan Nagib for the webinar of today. So Hassan, I stop sharing my screen, and if you want, you can start sharing yours.
Yes, thank you very much for the kind introduction, Francisco. And for inviting me. I also would like to thank Christos, who instigated this invitation. After a kind of a meeting at some conference. So I've been to Lille, and I wish I had arranged time to visit this during this talk, but as it turns out, Zoom is helping us. And I can see several of my good friends and some of my students, actually, because I'm teaching turbulence class this semester. Francisco, can you see my screen okay?
Yes, that's full screen, and we see your point as well.
Okay. There has been a number of collaborators on this work. In particular, I will start with work that Peter Monkewitz, who is at EPFL in Lausanne. And that's mostly on the asymptotics part. There are several contributions from DNS. Sergio Hoyas is the key contributor, Ricardo Vinuesa, and one of my own students who graduated and finished, but he's still in Chicago. I will show very briefly experimental results from University of Bologna pipe facility, and the collaborators there are Lorenzo Lazzarini, PhD student now, Gabriele Bellani, associate professor, another PhD student, Lucia, who graduated, and of course, Alessandro Talamelli, who's in charge of the facility. Let me then go to the next slide, which kind of motivates why I put this figure together. I'll tell you a little bit more, but this is the pipe in University of Bologna and Forlì. And I'll justify why we are it's about 1 meter in diameter and about 130 meters long. I will talk about boundary layers. This is one of the pictures at one of our wind tunnels here, and DNS pictures. All of this was part of a recent workshop at KAUST in Saudi Arabia, and it was motivated by looking at recent progress and also trying to motivate the work in pipe. I show you a picture of those. I won't name people except for the two key hosts. Peter Schmidt, many of you know him. He spent quite a bit of time in Paris. And Siggy, who has been at KAUST almost from the beginning. So maybe you can see some of friends in the picture. Now, let me start with some very fundamental things. The key in turbulence closure problem is to figure out some turbulence model, and I'm not going to talk about modeling today, to represent the Reynolds stresses. But for many, many years, nearly 100 years or so since Kármán, Pranttl's work, and then followed by Kármán, the concept of an overlap or log layer, as we talked about, and actually the log layer that you see here on a logarithmic scale is very small area down here in this zero pressure gradient boundary. I won't discuss today the roots of some of the values, but around the 1970s and 80s, the value of the slope, or 1 over the slope, which has been referred to as the Kármán constant, I will talk about that quite a bit today, was set at the value of 0.41. Most models, most codes, you still use that value. And the intercept for that log value of about 5. There are other values used in various codes. And that has been the picture for many, many years. Now you're going to be a little surprised, because I'm going to give you a warning before I give my talk. If, and it's a very big if, you will trust what I'm about to tell you today, and that was why we kind of planned the workshop to have a debate from the 30 people that were there on some of these things. And I've been encouraged to continue to kind of spread the message. We're going to have to make changes to our textbooks, lecture notes, RANS codes, turbulence models. I will also talk a bit about DNS resolution and time conversion. That came out as part of the work in the work. So I'm going to tell you now what I'm going to tell you, just so that you can watch for it. It turns out that the log layer is not the correct overlap, but there is an additional term, a linear term, which makes the layer much wider. Remember, I told you in the last figure that it was very small when it's only the log. The 3 parameters of the overlap region, which is still kappa, a different b actually, and the slope of the linear term are non-universal for different flows. They depend on the flow configuration, and they also depend on the pressure gradient. Mean and turbulence profiles are not sufficient to examine the characteristic of the profiles, of the flow of the overlap region. It is the derivatives, which I will continue to call today as indicator functions, are essential. So this requires that you need to make measurements, and you need to do computation that not only allow you to get the mean and turbulence profiles accurately, but also their derivatives, which is a big challenge with some of the old or even the current experimental data. Of course, PIV has been a big contributor. You will see that higher resolution and more conversion time than normally predicted in DNS is required for wall-bounded turbulence. And finally, that the Cyclope facility, which I showed you a picture, is really a valuable international asset to answer some of these questions. Francisco and I agreed. I'm not going to stop for questions during the talk, but feel free to put your questions in the chat to make it more efficient. Now let's talk historically and how we were lucky. When I say lucky, this was Jens Österlund and Arne Johansson from KTH, my own ex-PhD student, Michael Heitz. When we looked at ZPG boundary layers around year 2000, plus or minus, we found that this indicator function, which is the derivative of the mean velocity profile times the distance from the wall, You can define it on inner variables, you can define it on outer variables, has a very clear log part. These are increasing Reynolds numbers. When you look at the mean velocity profile, if you say, oh, this is the log part, you can always find on a log linear plot or log linear plot something that looks like a straight line, but its slope, the intercept, keeps a lot of arbitrariness. But when you take the derivative, and this data was good enough, and I'll tell you why, to allow us to do that. So at low Reynolds numbers, the green, for example, is not very long, but when you go all the way to this dark one, it's a, so, but then we were surprised also that the kappa was nothing like 0.41 in boundary layers, ZPG. Actually, later on, a few years later, in 2007, we pinned that value to be 0.384. And I'll tell you a little more about that. Now, so everybody got excited. We know more about the log law, and we know the coefficient better, so we only were able to do that because we measured the skin friction in both of these two experiments, at KTH and at IIT, using oil film interferometry. If you're interested, send me an email and I'll send you some papers. There continue to be a lot of literature. The key is measuring the viscosity of the oil that you put a very thin droplet. I mean, you cannot see it when you put it in, and I know people at Lille have used it. And you get the interferometric pattern from a monochromatic light, and you get out of that lines. We actually do it with different techniques now, but this was the original technique. Okay, actually, shortly after we had this data, Kapil Chauhan, who's now in Sydney, and I worked fitting mean velocity profiles from the super pipe, some of the data channel flow, including different ones, including the one from Erlangen, Zenoon, and Durst. The problem with the channel, I'll tell you a little bit more about. But basically, and then those ZPG data I just showed you. And what you see is the value of kappa is completely different between the three. So the red one is the presumably the channel, the dark blue one is the pipe, and the black is the, so the Reynolds number was high enough in pipe and boundary layers, but the channel is very problematic, and I'll mention some things about it. What is remarkable is if you plot kappa B versus B, the same kappa and B. This were based on the mean velocity profile using composite profiles. You get something that is very illuminating. It's a graphical trick. If kappa was constant, this curve should have been a straight line. The data here includes pressure gradient, boundary layers. A lot of these green data are from Notre Dame, actually favorable pressure gradient. There are many adverse pressure gradient. I think some of Lille data is in here. So so since 2008, we've been saying kappa is not constant. Now, it's very controversial because so far I'm talking about background still, not the new results. But this is the first part of the new result. This was published in August, JFM, with Peter Monkewitz. And I used this as the kind of the advertisement, or Francisco used it as the advertisement for the talk. If you do inner-outer matching of the mean velocity profile using one term outer, one term inner, this is what I call Millikan matching. You get the log law. It's tricky because once you get the log law, and for various reasons, it is very hard to add additional terms, but working with Peter and using a technique which is called block matching. It's not in any of the books on match asymptotics. The best place to find it is a paper by Dave Crichton. And again, send me an email if you want the paper. It's not easy. It's in JFM, but it's in the older scanned versions of JFM. Send me an email. I'll send it to you. So if you do 2-term inner and 1-term outer, suddenly you see the linear term. We like to use it, as I will show you, in outer variables. The reason when you do it in outer variable, the Reynolds number is embedded in big Y, which is the outer. So big Y goes from 0 to 1, while Y plus keeps changing with the Reynolds number, but they are completely equivalent. And for the ZPG boundary layer, we were so lucky because it will be the only case with S, this coefficient is equal to 0. So it was a pure log, and that is this case. I'll talk a little bit more about this curve. But you can already see that for a channel or for a pipe, the values of kappa and B are different. Kappa and S0, I'm sorry. All three, actually. Is this new? Actually, it isn't. You can go back in 1970 in JFM, there's a paper by Yajnik. He and his student, PhD student then, he's now a professor, Nur Afzal, wrote another paper. Both of these papers are very hard to read, really difficult to read. There is a simpler reference to it even in Lee and Moser. And more recently, Paolo Luchini has a physical review letter that brings it up. All of these four did talk about the linear term. However, they considered it a higher order term. And in fitting data, they ignored it. They left it out. And that they did not conclude that it was geometry or pressure gradient dependent, which leads to universal kappa. Today, I hope to convince you otherwise. So, one more thing, because I have a feeling some people in the audience, what happened to the power law that George and Castillo talked about for many years, and Barenblatt and so forth? Well, until about 2008, we were not sure if the log law for ZPG was, so this is all ZPG boundary layer. If you define C like we did, the indicator function, if there is a flat part, a horizontal constant, it's 1 over K. But if you define it this way, and by the way, you don't really need to consider this virtual origin business A. So even without the A plus, this figure would look the same. But basically, if gamma is constant, then it's a power law. At the beginning, when we were talking about low Reynolds number, like the purple or the green here, we couldn't quite tell. But until we got to over 10 to the 4 Re tau, this was the earliest experiment, was in the MDF at IIT, and suddenly we could convincingly show this was 2008. So, well, why was this confusion about the power law? It turns out that the answer is remarkably simple. When you look at the log, and here I'm using an example that I'll come back to. This is DNS of pipe flow. And I know it's a low Reynolds number, but it's just a demonstration here because we wanted it to be very good resolution. You can see how the points in the DNS and well converged. The overlap due to the log is this much. When you add the linear term, the overlap goes this far. And guess what? This part of the overlap looks like, pretends to be a power, okay? And it actually has the same thing down here. So when we were arguing about the power, we were more or less seeing the linear term, but not recognizing it. So I hope I got you to a point to be convinced that we need to check on this linear term. The best place to do it is in DNS, for reasons I will explain. This is my favorite DNS by Lee and Moser, and not because they're both my friends, it's just because we, as I will conclude later, it's with sufficient high Reynolds number, 5200 RE tau, and it was well resolved and reasonably well converged. Actually, it could use more conversions, but it was a very expensive DNS at the time. So when you plot C here, again, I'm reminding you, see, if it is horizontal, then it's a log law. I remember when both of them contacted me, I said, hey, we got 0.384. I couldn't believe it. I mean, and then I responded, I said, but based on our latest information, you shouldn't get 0.384. Well, if you fit over a range, and I'll talk about the range of y between 0.3 to 0.5, you see this orange part with a linear, and I'm going to use this type of figure so often, so I want to spend a minute here to explain it. You get S0 now, oops, sorry. You get S0 from this slope, and you get kappa from the intercept, because your equation has 1 over kappa in it, and that's the intercept in C, and S0 is the slope. You can see why we use outer variables, because you don't have to worry about RE tau. It's all straightforward. Everything else is higher order term. Okay. So let us now, in the paper in JFM, when we compared using experiments and so forth, other DNS of channel, we concluded these two values. From this figure, you nearly get the identical values. Okay? Now I'm ready to show you the figure that I showed you at the beginning quickly. So beta is the pressure gradient, and it's defined using outer variables. So it's not a beta that you use in adverse pressure gradient boundary layers where you use delta star. You actually use big Y. So for a channel, it's -1. For a pipe, it's -2. And for a zero pressure gradient boundary layer, is 0. You can see there are two types of data in here. The red dots are the DNS. Actually, I'm sorry, the red are the experiments, and the blue are the DNS. The channel DNS has had a lot of issues. I'll come back to it in my talk. But anyhow, what you see very clearly, we were very lucky, and you've seen this figure before in terms of its kappa being constant and for zero pressure gradient, but that's the only case. And beyond that, you need the unit. And all three of them are non-universal. I won't talk too much about pressure gradient boundary layer today, but we have analyzed all of them. Now, believe it or not, and I need to check on my watch, yeah, this is the message of the talk. And at the bottom here, it says it. Why am I using channel flow data here today? And some pipe is because channel has the largest database. Pipe flow is our ultimate goal. Why is pipe flow our ultimate goal? It is not possible to have a truly two-dimensional channel facility, channel experiment. And to do DNS for span-wise periodic channels is a headache by itself. And it's not going to match the experiment because the channels develop in length and they develop side to side. Boundary layers, it turns out, it's very difficult to do setup in zero pressure gradient boundary layer. There are actually 3 tunnels that have succeeded: Melbourne, KTH, and IIT. Other tunnels, it's very tricky. It's like a pendulum. It's easy to do adverse and favorable, but ZPG is very tricky in between. And I'll show you that in DNS towards the end, boundary layers have zero pressure gradient boundary layers have some serious issues. So the fully developed pipe is really the best place which you can do compatible experiments and theory and DNS, and the Cyclope facility in Bologna is a very good. There was a lot of a good place to do it. There's a lot of talk about the singularity, but recent work by Pirosoli, Sergio Pirosoli, by Philip Schlatter, and Fazli Hossein, and others, and our own, I'm going to show you, have dealt with that. It is computationally demanding. It takes about 4 times more than the channel, but really this was my final message, is that fully developed pipe is the right place to do DNS and to do experiments. So we're not telling people stop doing channel, it's just encouraging more pipe. And the experiment is a key. Now, you should ask yourself, for someone for decades focused on ZPG boundary layers and experiments, why am I using primarily in the next remaining slides DNS? Well, the reason is with DNS, I can calculate the indicator function more accurately. I can differentiate the data and get the indicator function. The experiments, there is, as I said, PIV has made recent strides, but otherwise. Okay, so now I start showing you about, I don't know, 10 slides with indicator functions, so I won't be switching. Remember, the indicator function is defined easily, and most people have plotted it with this kind of scale from 0 to 6 or so. And the gray line here is actually the Lee and Moser, and they thought 0.384. But there is a problem with this data, as I'll show you in the next slide. You're not focused on the errors in the range. So if you, oh, I should define which data. This is our own at 550, Lee and Moser. This is Sergio Hoyas at 10,000. This is Jimenez and some of his students. Hoyas again, lower Reynolds number. Yamamoto at 8,000, and the most recent Yamamoto was actually a channel at 16,000. It's not published, but we have had the data for some time. This is the scale you need to plot the data. And you can see, using a plus or minus 5%, none of these curves, except for a very short log part in the Lee and Moser, none of them have flat. And remember, an overlap in asymptotic expansion needs to start for all Reynolds number, for the range of parameters, at the same inner variable y plus, and end at the same outer variable. They don't end at the same outer variable. There is not even a log. So that's just the statement I made, expanded a little bit. The outer variable and the inner variable don't start. This is the inner. They don't start at the same point. There is no straight line. There are 2 experiments, have 2 DNSs that seem to agree, and they don't end at the same y. So we wanted to know something about why those DNSs and the conversions and so forth. We also wanted to do pipe DNS. Mostly Sergio Hoyas and Ricardo are doing this work, and it's using a code that's available from Ashley Willis. I've never met him in person. Maybe I met him, but I don't remember. It's very impressive code. And he's at Sheffield. The code is available. You can go to this website. But we made sure the pipe is much longer than the one Schlatter and Phys. It's 10 pi. We do the full range. And also the Yao, Schlatter, and Hossein is what we call our low resolution. So this is the DNS points in delta. It's delta R actually, plus, but because I include the channel. You see in the channel, you can, as you go away from the wall, you can get it big, but in the pipe, you have to go to the center line. That's why I said earlier. So we ran 4 cases with different radial resolution and different azimuthal resolution. And theta we run completely 0 to 2 pi. I will guide you through them, but the red one, think of it as the true or correct. Sergio Hoyas and my student Victor did a fantastic job analyzing. The data actually is done on the fly with all information that you see here, including kappa, S0, and B. They come out from the data for every step of the computation. So you run the computation for a long time. The red, remember, is the standard. All of them agree in the mean velocity. Remember, this is channel. Okay? I'm sorry, this is pipe. Maybe because I'm going to switch to channel in a few minutes. So this is low Reynolds number, so you will see, but we also have 1000. I'll show it to you. Reynolds stresses look fine, but when you do the indicator function, if you can see carefully, you can see the red one is coming up here. So I'm going to go to the next slide. And the picture looks very different. The red one is by itself. That's the highest resolution in both radial and azimuthal directions. And since you need to use this part of the curve of C, of the derivative, you need to fit a linear part here. By the way, by the Reynolds number increase, this linear part gets bigger and bigger. And so if you fit that and you plot, it turns out that the convergence is not just the resolution is a problem, but the convergence. Most DNS data stops with Eddy turnover times down to here. The reason we ran this low Reynolds number is because we actually ran up to 200 Eddy turnover times. I show you up to 90. They never converge. They don't, and that's a subject we're still being careful. So Sergio wanted to make sure this is not an effect of the code. This is not an effect of the Reynolds number. So we went to channel using his code, which is really based on the heritage of the Jimenez code and so forth and others. And we went up to 1000. This is hot off the press in the last few months. Actually, it was first presented last month at CAUS. It's a channel with many different, he ran all of these cases, box sizes, that's the box size, NX and HX, NZ, and DZ cases. The standard one that you see in DNS is this purple one. I also will show you these 3 green ones, and they are decreasing ETT. So this is the long and eddy turnover time and so forth. How do we test the convergence, which is really a difficult issue? We calculate an epsilon between the expected mean shear, which is the linear shear distribution in the pipe flow or channel flow. This is channel, compared to what you get from the DNS computation. And you integrate from from 0 to H0 to H plus, or from 0 to R plus. So you do it. So for the channel, you can see, I told you this is the most common standard one, but some of the cases, they're not very well converged across the difference. And then when you integrate this, you get this number, and the different green ones, they only reach the 10 to the minus 4. But it's still, most of them are okay in conversions. Now, profiles are also okay, except for the peak near the wall. So this is one normal stress. I'm not showing all of it. That's one shear stress. Outside, it's within 0.5%. That's okay, except, so all the debate about the near wall peak, there is too much uncertainty due to conversions and resolution. When you go to differentiate the mean velocity to get C. Remember, I told you I'm going to keep using this figure here. 3% differences between these cases. The true one is the purple one. Oh, the best, close. But resolution and conversions are all over. So keep this in mind as we're going further. I also show something I will talk very briefly about today, and that is the indicator function of the normal stress. And that's even more all over the place. And again, you have to always plot things with the right scale. So now I'm ready to start wrapping up the seminar with the main highlights. So I look at the channel, and I want to tell you how we define this range. 0.3 to 0.5 appears to be very robust for all the Reynolds numbers we've looked at. I keep using the same notation up to 16,000. And there is some sensitivity, but we test for getting different values for the inner and the outer edges. This is the overlap region, and it grows. If you really want to know how we systematically did that, there is this figure in the JFM paper I mentioned last August with Monkewitz. But when you do that, the slope gives you, and here is what I wanted to give you a warning. I'm not going to give you the Reynolds numbers in values. I'm going to give them to you in color. The lowest Reynolds number is the red and green. Then it goes to the gray. Then it goes to the black, then to the orange. And then it goes to the blue. The blue is the 16,000. The 16,000 appears to be no more information in this region than doing your DNS at 550. I won't get into this discussion, but now because of the time limitations, but I can tell you some aspects of it. Here is really the punchline for the talk, or the beginning of the punchline. The big problem when you do, and remember, I'm showing you everything DNS here today because I can differentiate accurately. You're actually looking at direct derivatives. Carefully done, we use higher order derivatives and so forth. But you can see the channel grouped and the pipe group. Solid lines, channel, dashed are pipe. The channel is closer to a log law. So in all these years we've been doing channel, yes, you can kid yourself and say, well, uncertainty, and especially with the experiment. The pipe is very distinctive, okay? And you can see that the kappa for the channel is 0.4, very close to what we found in Monkewitz and Nagib. For the pipe is 0.445, and the corresponding S0 is much bigger for the pipe, so that's why you get this slope. Next, I look at the pipe, and because I want to extract the best values from here, and I come up with 0.45 and 3.3, and it's clearly away from the log. The log plus or minus 5% is here, and the log plus linear plus or minus. How does it compare to experiment? I promised you not, oh, I should make one conclusion. I said it already. I'm sorry that you cannot see it here. I don't know if I can actually move this. Yeah, maybe you can. In my opinion, we spent too many years and CPU time working on the channel because the distinction, the discrimination between pure log and log linear was not sufficient. Okay, now when you go to the cyclopia pipe, and you can see how long it is, and I'll show you another picture. Actually, I don't include that picture today. I showed it to you already. You can follow the centerline velocity, and it takes a little explanation, but the centerline velocity plotted on log law gives you kappa also. And the average value is 0.435. I'm going to show it to you again. Within 0.5% accuracy, the early experiments by Fiorini and Mascotelli, and the recent experiment by Lorenzo and myself last April, 3 different runs here are in excellent agreement, and that's the kappa value. I don't compare the B because it gets, the S0 gets a little, oh yeah, I do show you. Here's Peter Schmidt, by the way, and that's Lorenzo, PhD student, and this was last April. And when you take the centerline value, the kappa is nearly identical to what we put in the paper. The S0 is different, and to be honest with you, I'm not sure about that difference yet, and I need to understand it better, but they're still not zero. S0, it's not zero. It's far from being zero. So looking at the channel, we get very good agreement. Looking at the pipe, we get disagreement, 0.435 to 0.44. It's really interesting. That's the pipe value that Zagarola and Smits, actually Lex Smits is in Melbourne, and he wrote me, he said, I'm sorry, I'm gonna miss your talk because the time is, I'm sleeping. But Zagarola had the right number, which is really remarkable, how many years ago. Okay, just a minute or two on a completely different issue, but it's very controversial right now in the literature. So if you know it, you will follow me. If not, ask me a question, I may be able to. This is doing the normal stresses, the UU stresses, and you differentiate them with an indicator function. I call it zeta. If you read some other paper, they call it, but I call it zeta to make it different than C. If you do the simple derivative, that's the indicator function. You plot it with outer variable. If the ideas of the attached eddy and so forth are correct, you should get a log part. A pure log, but remember, it must start at the same y plus, and it must end at the same big Y. Well, they do seem to end at the same big Y, but there is no log. Now, Srinivasan, Chen and Srinivasan introduced a different approach based on bounded dissipation, and instead of a log law, they find the 1/4 power. If I take that same plot and convert it so that I can see where is a 1/4 power, it's again, it's a graphical representation. For those of you I can see it, I mean, all that I do is just multiply y to the 3/4 here, and especially at high Reynolds number. Now I'm going to define the Reynolds number for you. You see a very clear overlap region, but it's 1/4 power. It is not log. These pipe experiment low Reynolds number by us, Hoyas, and with the Willis code. Then they go, all the dashed ones are different channels, different pipes. The channels, I continue to use the same colors. The gray is Lee and Moser. The black is the 16,000. The blue is the 8,000, both of them from Yamamoto. This is Hoyas at 10,000. But the pipes include the Yao and Schlatter, Philip, and Fazli. They also include the Perosoli. The P is for Perosoli. And the colors are the same. Once you get to Reynolds number of about 1,000, so this Reynolds number, and you don't gain any more in the channel by going to 16,000, okay? And that's gonna be one of my messages. Last 1 or 2 slides. Remember, I showed you before that ZPG, when we did it with experiments, we got this growing log region. So we go to DNS with ZPG. This is again, Schlatter and Urlo, Borel and Siloro, Hoyas, a number of cases. And these are all ZPG. Then these are APG, adverse from Ricardo Vinuesa's group in KTH. The student's name is somewhere here. Oh, here is a Puzulu. And you plot C, and you tell me if you see any log law. You don't see it. They seem to be down here below y plus of 100, but nothing in the traditional. Well, what's the problem? So we look with a microscope at the ZPG and the APG. Why do I include the APG? Because for APG, I can tell where the wake effects start. So my overlap for APG and for all boundary layers, you see these values are much smaller than in pipes and channel. Instead of 0.3 to 0.5, they're from 0.05 to 0.2. And we can have discussion about that, or email me, and we have some papers that I can send you. So I start focusing on this area here. And I go look at ZPG alone. When it's low Reynolds number, you can see it doesn't get to agree, but once you get to 1,000, Arital. By the way, these are not Aritals, these are Arithetas. Okay, these values here. So when you get to about Arital, they all agree, and they give you a value of 0.49 of kappa and 4.8 for the slope. So this is not zero. This. Finally, why is that? I don't know if you can see my hands, but I'll try. The computation starts with a laminar boundary layer. You trip it, you compute, transition it, you compute to high Reynolds number up to, this happens to be Orloop and Schlatter, up to 10,000 or so, but you stop here in examining the data. Here is the range. Then you relaminarize, so you can use periodic boundary condition, and you recompute. I have no problems with that. I've always, and I had many discussions with Rames and Philip and so forth. This is perfectly fine. The problem is with the top boundary condition. The bottom, of course, is the wall is very easy. You need to aspirate the flow to allow the boundary layer to grow. In APG is not as problematic. ZPG is supposed to be parallel flow near the wall and then growing. So near the wall, you neglect the advection terms. Actually, the student who pointed this to me in class was earlier on the Zoom call, but he may have left. He said to me, you just told us du, dy near the wall is very large. How can you say it's much smaller than the viscous term? I said it must be controlled by the v velocity. So what I'm going to do in this slide and the next slide is to look at the dp dx and the v's. So here is beta, by the way, and you notice in their calculation, beta is not zero. It's actually favorable. And if you expand this curve, all what you do is just expand this range, you see that constantly the dp dx is changing. Well, what is this doing to V? And again, I compare it to APG. So this is the mean V from 0 to the edge of the boundary layer. Forgetting this low Reynolds number case, they're quite substantial V's. Oops, sorry. And they are not much smaller than, and you know the APG is the boundary layer is getting grower a lot more. If you compare them on a log scale, log, it's only one order of magnitude different in this UJ. In channel and pipe flow, the V is machine accurate. If you're using double precision, it's 0. It's 10 to the minus 16. While here, we're looking at 10 to the minus 3, 10 to the minus 2. So I'm ready to conclude. I'm sorry that it took me 5 minutes longer. Millikan matching is not the recipe that one can follow. only boundary layers. When you do the full, you get log plus linear. This is the full asymptotic. Well, as full as we can deal with it. All other terms are higher order. And if you ask me the question, I might as well answer it now. The higher order terms all have 1 over RE tau in them. So they just disappear as RE tau grows. They're non-universal. ETT, Eddy turnover time, needs to at least get to 20 to 50. We're not quite sure if there is an exact recipe here. You also need to use higher order computational methods. The Willis code actually uses, and the Hoyas, between 7th and 12th order methods. The values for pipes and channels are different. This is pipe, channel, channel. This is maybe my most important conclusion. It is more important and fruitful to perform highly resolved conversion, very expensive, that means, DNS with higher order codes in an adequate size domain than to chase higher Reynolds number. And you'd ask me, what range do you recommend? I think maybe by luck or by careful, Lee and Moser have it right. Between 2,000 and 5,000, depending on your other aspect parameters, we think is adequate. We don't need to chase beyond that. You need to get derivatives, and experiments require more. So I better stop here, and I'll let questions come after that.
So thank you very much, Hassan, for the very interesting talk. As you said, of course, let's go for a question. So whoever would like to ask a question, just feel free to unmute your mic, or you can write in the chat, and I can report your question. Let's see if there are some. Then I maybe can start with one, actually. So it was about basically the whole message of one of the most important messages of the talk is the non-universality of the coefficients, of the two coefficients, of the log part and the linear part, right? So if we want to look it into a modeling perspective, this is basically suggesting that canonical geometries, okay, can give us an indication of how these coefficients are supposed to work in simple geometries, but how much predictive value do they have on complex geometries then?
Big effect. When we looked at boundary layers and we have those results, I don't think I have time to talk about them, but they change quite a bit, even in pressure gradient boundary layers. So this is going to be an open question for future research. And it is, you asked sort of the holy grail question. So if you want to use models that depend on the mean velocity of the overlap, we need something else. This kappa B, by the way, curve, and that I can show quickly from the other results we have, depending on questions. But the answer to you cannot have a simple recipe. No. I see James, my good friend James Brasseur, raised his hand.
Yeah, Jim, go ahead.
Hey, Hassan, how are you?
Good, how are you?
Where are you right now?
I'm in Chicago right now.
Oh, okay. I just came back from Chicago. I went to the solar eclipse sighting. Anyway, I just want to ask you, okay, so, you know, the Millikan approach, of course, has been often used. I tend to like to think from a much more physical perspective, and I think of the log region as a region where to get a log, the mean velocity profile scales on a single velocity, which is the friction velocity, and a length scale, which grows linearly with the distance from the surface, and that integrates immediately to a log. If you're talking about a linear term, what's the corresponding physical description of that linear term?
That's a great question, and I never like to say this, but You both asked really good questions. So all questions are good questions. So there are many, many ways to get to the log law. In fact, Tanakis and Lumley have a way, which I don't particularly like it. It's in their book. What you said is kind of what the Marusek and Perry and Min approach to doing this with the linear scales and so forth. And they get a constant kappa. You need to have that for the attached eddy model to be confirmed. But there is obviously a contribution that makes the scales not grow linearly with distance to the wall. And that we still don't have the way to incorporate that yet, although we're talking about it. But obviously, it was too simplistic. Now, the harder question is what happens to universality? Because once you add the linear term, that is so. Those are very serious questions, and I don't know if I have enough years in my life to devote, but I certainly, whatever we can do, and I'm spending some time with Ivan and his group, and hopefully we will look at this. And that was a lot of discussion in this KAUST workshop that I talked about there.
Okay, so how do you know that it's deviations in the length scale rather than deviations in the velocity scale?
We hope that PIV will give us that. One of the reasons Cyclope, and I say PIV, I'm not talking about the classic, I'm talking about the Tomo, and I'm talking about the particle tracing, advanced concept. The Cyclope tunnel does not reach the same Reynolds numbers as Lex's super pipe. It's an order of 10 less, but it gives you much better spatial resolution. And there are 2 test sections actually being fabricated. I'm in for Lee next week to do Tomo PIV and to do LDV. And careful measurements, and not only near Y plus, we always used to, Jim, focus on, including myself and near the wall. We need to do now 0.3 to 0.5 is a good part of the flow. We need to document everything.
Okay, thanks. So can I ask a related question, unless somebody else wants to?
I'll leave it up to Francisco. I'm open, and you can always reach out to me on phone or email.
Yeah, Jim, go ahead.
Okay, so you're obviously, I know you're aware of the atmospheric boundary layer work. And one of the things that I've always argued for many years, and you've heard me argue this, is that these 2 communities need to get together in discussing issues like you're discussing right now. But there's that well-known paper by Andreas et al. In 2006, where they measured, well, he used all the data available in the atmospheric boundary layer. And of course, there's issues and so on. Don't need to go into that. But he came up with a von Kármán constant, best estimate of 0.387. I'm looking at the paper right now in front of me. And I often would quote that number.
I'm familiar with the paper, and I agree with that result. Yes.
Yeah, exactly. That's my point, is you agree with that result. After having published previous papers saying that, well, you get different results depending on the flow and so on. And now you're coming up with a number that's really quite close to his in the atmospheric boundary layer. But of course, the atmospheric boundary layer is a rough wall boundary layer, not a smooth wall boundary layer. So you don't have the viscous region that you spend a lot of time talking about with the overlaps and all that. So just very, as briefly as you can, obviously there's all sorts of issues with the roughness. There has to be uniform roughness. The thickness of the roughness layer has to be very small compared to the log layer, and so on and so on. But assuming that those conditions have been met, do you see other fundamental differences between the smooth wall and the rough wall boundary layer?
If I recall correctly, they only looked at neutral conditions and not very rough. I mean, if you're talking about atmospheric boundary layers that are coming from or going into urban areas or heavy.
No, I'm not talking about that. I'm talking about the same kind of classical canonical cases that you talk about.
Yeah, then as I said, ZPG boundary layers in the laboratory 0.38 or thereabout, 0.39. The best number we have is 0.384, which is very close to theirs. So there is no disagreement. The roughness effect is not clear, and we want to look into that now.
Well, when you do, I make a request that you don't do it independently of the atmosphere community.
I would love that you can be the conduit. I used to know a lot of people in the atmospheric community. Unfortunately, some of them have passed away. So I'll reach out to you. But I see that two questions. Let me answer the one very quickly in the chat. The information from the two, the mean and the statistics, was contained in my answer to Professor Brasseur, James Brasseur. You need to have the two compatible. So, but I focused on the easier one to do today. But Surab has one question.
Yes.
Francis.
Hi.
Yeah.
Please go ahead. Yeah.
Hi, Hassan.
Hi, how are you?
So regarding this two-term inner matching with one-term outer.
Sorry, try to speak a little bit louder because we don't hear you.
Can you hear me now?
Go ahead. I can barely hear you, but go. I will repeat your question. Go ahead.
Okay, so what you're doing is you're matching two terms in the inner with one term in the outer.
Two inner and one term in the outer, correct.
Yeah, so if you look at the classical matching procedures, for example, if you go to Van Dyke's book on perturbation methods, you know, what he prescribes is after you do the first term matching, you then include two terms in the outer expansion first and match with the one term in the inner. So is there a theoretical basis for doing two terms in inner with one term in outer?
Yes, I did this very quickly. So let me repeat it now. That's an important thing to state again. When you end up with one term matching with the log, it makes it, you know that, I know that you know, it makes it very difficult to include higher order term, except in aeroacoustics. That came up many years ago, and David Crichton and others, David has passed away. And if you send me an email, I'll send you the paper, wrote a paper where they call it block matching. In block matching, by the way, block matching is not found in Van Dyke's book, in Knife's book, in Cole's book, in Panton, and none. You have to go to that paper, and that's what we used.
Okay. So, and you feel that that's more appropriate for turbulent mean profiles than other methods?
Look, you can do matching in I tell my students, and I don't know if any of them, they had to go somewhere else, but they were on a Zoom call earlier. The answer is kind of as good as what you get and what is the higher order terms. Yajnik's paper found the linear term, Afzal's and Yajnik's, but they assumed it to be a higher order term because of the way they did it. Block matching really makes the difference. So I think this is kind of a, and feel free if you want to have a separate Zoom call, we can arrange for that.
Yeah, okay, sure. And just a related question. In the classical matching, you know, the overlap region, of course, you get a log law or power law, but then you also have a special feature that the Reynolds shear stress is a constant. That's a peak Reynolds stress region. Now, in your approach, where you get the overlap region to be much higher in Y, you know, starting 0.3 or so, is there any characteristic of shear stress accompanies this?
Yeah, I referred to that very quickly. In Tannaka's and Lumley's book, they actually start to develop the log law based, and I know Jim Brasseur, and I think we've talked about this in the past, you start with a constant shear stress, and then you get the log law. The conclusion that the shear stress is constant is a bit of a tricky, based on the Millikan matching, the strict Millikan matching is a bit of a tricky discussion, which I would need Peter Monkewitz to be on the Zoom call with me to have. Okay?
Okay, sure. Okay, thanks, Hassan.
Thank you.
So thank you. Is there someone else who would like to ask a question? Just once again, feel free to unmute your mic if you have any question, or you can write in the chat and it can help. So that doesn't seem to be the case. May I ask you a last question?
Please do. Please do.
Yeah, so whenever you say that you suggest basically you identify the sort of range for the Reynolds tau to carry out DNS, and you suggest that that's the range which is supposed to be the best candidate for carrying out DNS. Do I understand it right? You identify that range based on the convergence of the two fitting parameters. So whenever
It's
that
actually, yeah, it's actually an optimization kind of issue. You shouldn't go beyond the Reynolds number where your resolution is adequate to not only give you good mean values but derivatives. That's true. That the order, because the higher order methods require more computing time. So, and that the computing time is available to you to converge. And the big question there, what does it mean, conversions? What are the conversion tests? I showed you one today. We have another one, but it would take too long to. And the computer time you have and your physical time. I mean, I think if I remember right, M.K. Lee took about 2 years of the Argonne computer to, over 2 years he was running in order to get his results. So you need to optimize. Yamamoto and I, when we talked, he got to 16,000. He's going to try to run longer conversions. But one of the issues, his method is a second order.
Yeah.
So we encouraged him to look into both these things. And because he said, and he has access to possibly one of the world, more powerful computers, top 2 or 3. And he said he just does not foresee getting that kind of computing time and that many processors. And actually, also, we asked him that question, and I'm answering for him. He said GPUs, which are available on that computer, didn't improve things because it's the transmission times that kind of kill the running time. So that's why we're saying, if you can, by the way, we have not done those tests fully for Reynolds stresses, but we've done some of them. I showed you that above 1,000, they don't seem to change the derivatives. And the other conversion test that we use involves derivatives.
Okay. Yeah, I just asked the question because the point for me was like, okay, as far as I understand in terms of asymptotic reasoning, is that the higher order terms in Reynolds tau, they basically are supposed to fade out as soon as you go to higher Reynolds numbers. But this is I expect that they fade out differently depending on the kind of flow you get. So maybe this range can be shifted depending on the flow you have, like if it's a ZPG or an adverse pressure gradient or pipe flow, right?
Correct. Actually, I have some slides. I took them out. We tested the approach to convergence of the mean flow and of the normal stresses. We started with the assumption that the mean flow will converge first, then the turbulent. And it turns out, crudely speaking, I mean, there's not, and you're right, it will depend on the flow. We did this for pipe flow. We actually, I think Sergio also did it for channel. They don't, they converge about the same rate. You get to the equivalent convergence in the mean and the normal stresses at the same time.
Oh, interesting. Oh, that's okay. Okay, very good. I didn't expect that. So thank you.
We didn't expect it. We didn't expect it. Yes,
Okay.
that was a big surprise to us. And I have presented that.
I see. I see. It would be interesting to understand the reason why, because that's quite an impressive point. That could be eventually a feature of universality in the decay of in terms of Reynolds number. That
I would love to on my next trip to Europe to stop and see John Paul and Christos and you, and we can talk. We can show you some of this data, and it's ongoing right now. We got deviated because we needed to do other things. This business about the bounded dissipation versus the and by the way, in the workshop in Kaust, Srini and Ivan agreed that the nomenclature attached to Eddy model is not a good one, and they talk now more about near wall scaled models. Yeah,
I see. I see. Oh, very interesting. Okay, so I think we had a very lively discussion. So thank you very much once again, Hassan, for the interesting talk and the availability for the discussion.
Thank you. And please send me the link when it's available. As I said, some of my students had to leave early because I have a different class, and I would like to share it with them.
Definitely, definitely. So I invite our audience to thank our speaker of today once again, and hope to see you for next webinar. Thank you once again, Hassan.
Thank you, Hassan. Thank you.
Thank you, guys. Thank you.
Bye. Have a good evening to everyone, and Hassan, and on the other side of the coast, have a good day.
Thank you. Thank you.